stuck behind my car at the hotel so that I wasn't going anywhere until they left.
Oh, okay. So I posted homework, and I'm planning to have 2 homeworks due. I mean, it's just I split it into 2 homeworks because it's different content, but it's about 3 problems. You think that's reasonable? It's on 2 different topics, though. Did anyone get a chance to look at the homework? It was done only in the morning.
No,
Yeah.
because I checked last night and there was nothing else.
Yeah, I just did it a few hours ago. A whole box last time. Over very quickly, I guess. So there's homework 5, which typically deals with problems like what you have seen earlier in Lagrangian mechanics, where you given a pendulum, write the Lagrangian, write the equations of motion, and so on. I typically give about 3 to 4 such problems in the homework, and I make it long and do the small angle approximations and so on. But this time I made it only 1 problem. So it's significantly condensed. Instead, I added a question on Lagrange multiplier. There, the advantage is that there is this notes I have from last semester. So one of part of your homework is to go and either refer to the lecture from last semester or use your own resources and do the problem. So there is 1 problem again to do, but probably the easiest probably is to do the look into the lecture and then do it. So it's at 45 minutes video, probably you have to look into it. So it's part of the homework. So hopefully you find it reasonable. So you, after the spring break, don't remove the spring break from it. This is not because I want you guys to work during spring break. I do enjoy your spring break, but it turns out it is. So both are due same time. This is on Lagrange multipliers. And this is on standard Lagrange. And this is on, you can call it, this is on small angle approximation. Hopefully I can finish that, but even otherwise, I think it's can be done based on the homework because I split it into so many steps. So 2 weeks. I think 2 weeks after we come back from spring break, we have midterm, probably in the third week. I guess. 14th, 28th, yeah. What, the okay. Just mentioned your name and you came in here almost hearing me. Okay. So we have at an abstract level or at a very generic level, we have introduced the idea of Lagrangian. We have introduced the idea of Hamiltonian. Usually the standard problems are often there is a lot of time spent on given a physical problem, determine the Lagrangian, write the Hamiltonian, get the equations of motion and so on. So I'll do a very simple exercise today. Next time we will do a more complicated problem, which is a double pendulum, which doesn't have exact solutions. Like today we will do a simple pendulum, which has actually that also does not have exact solutions, correct? Only for small angle approximations you have exact solutions. So we will do small angle approximations, get exact solutions. Do the same thing for double pendulum, where again, if you do small angle approximations, it turns out that it is tangible or it can be handled reasonably. So the main idea here would be, since at least from what I have seen, these problems are often covered in other courses, the small angle approximation part is the more, or I would like to emphasize on that, and how in complicated systems, small angle approximations really help. So let me begin with the example of simple pendulum. I should change this. So the example, let's say, simple pendulum. I think I've asked this before. Why do we call it a simple pendulum? What's the difference between a pendulum and a simple pendulum? I personally don't know. Yeah.
I think it's because we ignore any contributions from the string, any mass.
Oh, okay.
So it's supposed to be a
Just at the
mass
end.
At the end of the mass of string.
That's a compound pendulum is when you have other. Yeah, I see what you're saying. If you have
If there's a rigid body, where you might have like you're using a rigid body.
Got it. Yeah. Okay. Is that? You know what? I think simple pendulum is when all the mass is concentrated on a point, the end of the length L, and the string itself is mass. That makes sense. Yeah, very good. Okay, so so the system is clear. So we have a let's say a ceiling, a very specific point, and we hang a string. It doesn't, if it is under gravity, it doesn't really have to be a rigid string, but it is good to have a rigid string if you're really talking about going, if the angles are large and you really want to go more than θ/2, and it's good to have a rigid string. Well, let's say that's length L, smaller. Right? So that's angle. So θ is measured positively with respect to the negative y-axis in that sense. And it is the only force is gravity acting downwards. And the idea is we want to get the equations of motion. Very simple exercise. We know what these equations are, except that most of the time we already assume that this is a small angle approximation. So we can keep that. But even otherwise, what we want to emphasize here is what exactly does Lagrangian loop do, right? What is the, in what spirit is the Lagrangian able to capture the dynamics here? So first, let's go ahead and do the standard Newtonian mechanics. That might be a good just for comparison. Let's say there are how many forces acting? There is gravity acting downwards. And is there any other force acting on this? On that mass M? Tension, right? Force of tension. And that's, if you notice, the force of tension is almost like how do you say this? Yeah, so I think it is called that. So the way the problem is described, the mass is constrained to move on a circle of radius L. And the job of the tension force is to make sure that that is what happens. So in a sense, T will be called the force of tension. Let's say T will be a force of constraint. That constrains the mass on a we are already assuming that this is all in a plane. In general, that it is possible that this could be a spherical pendulum, right? There is another possibility that this same pendulum is free to move around on a sphere. And that will be part of your homework, actually. One of the problems in your homework 6 is where this pendulum is free to move around on a sphere. But there we are interested in the force of constraint, so we won't do the dynamics so much, but except the Lagrangian itself. So that here we are assuming that it's on a circle, so that constrains the mass on a circle of radius L. And once you have a constraint like that, always the force of constraint here, the force of tension, will be perpendicular to the constraint equation, if you want. In this case, it's not a sphere, it's not a surface, it's a circle. Perpendicular to that circle at every point, that's the force of tension. So that's the idea we want to capture. And that kind of a constraint, whenever you have that kind of a constraint, Lagrangian helps. So it will get rid of those constraint force altogether. Otherwise, tension is often, it has to be expressed in terms of material properties and so on. It's a model, basically. So it tries to get rid of that force of constraint completely out of the picture. And this is crucial in general when you work in other systems. For example, when you talk about electrodynamics, there is a constraint on the magnetic field. What kind of constraint is it? So when I say that the magnetic field is constrained, what kind of constraint can you imagine in electrodynamics? Can any vector field be a magnetic field? So there is very special properties that magnetic field obeys. That's a Maxwell's equation. But which particular Maxwell equation is really a constraint? If you recall, there is no monopole, that's del dot divergence of V is 0. So not every vector field is a solution for magnetic field, only those that are divergence free. So that's a constraint. But you don't want to, so when you have that equation, it seems like it's an additional baggage you have to carry. You have to think about all functions. So if that is a function you can think of which only constrains only those kind of problems, that really helps. So whenever you write a Lagrangian, it automatically takes care of this kind of constraint. So there it is a much more complicated system. Here it is much simple. It can be interpreted in mechanical terms that there is a force of tension, but notice the Lagrangian doesn't have force of tension. If you have seen the Lagrangian for the system, it will not have a force of tension. So the idea is that you get rid of those kind of constraints, which is not really fundamental, that is forced to keep. So that's broadly the idea of Lagrangian. Get rid of the constraints and give me only the interesting part of the system. Don't give me all the details in it. But let's go back and first do Newtonian mechanics where there is a constraint force. So you would say, how do you go about this? Let's see. So help me here. So how do you go about solving this problem? So which is the coordinate system used? So let's have a coordinate system of this kind. So this is radially outward, and let's say that's tangential, right? So that's theta hat. So that's a circle, and on that, this is theta hat is a tangential vector. R hat is a radial vector outward, and then break the components, right? So that's your so mass times acceleration. So Newton's law says that mass times acceleration has to be the sum of the forces. There are two forces. So that's mg plus the force of tension. Right? That's the statement of Newton's law. And then you want to break this equation into the radial direction and the theta direction, right? So that's r hat in the direction of r hat. So let's ask what is the acceleration? So that's mass times acceleration. Let's say the radial acceleration is equal to, if this is angle theta, that's angle theta. So it is mg cosine theta. It's positive mg cosine theta in the direction of r hat, and minus t. That's your force equation in the radial direction, and in the direction of theta hat, it is mass times acceleration in the tangential direction is equal to minus mg sine theta. And that's it. There is no force of tension in that direction, correct? And now we say, what is the radial acceleration and what is the tangential acceleration? And we quickly have to derive that. So let's say R itself, the position of the mass m there, that's equal to L times R hat, right? That's the position of the mass with respect to that coordinate system. It's a length L. How far you're, that's the position itself is length L. It's always length L, and in the direction R hat. So we want the acceleration. So velocity to begin with is the derivative of this. So that's L. L remains constant. So it's the R hat over dt. We can do this geometrically, but it is good to see that R hat is equal to, so get this triangle if you were to draw. So this is your x and y coordinate is this. That's your x and that's your y. This is in the fourth quadrant, right? So this is equal to L sine theta, I guess, in the direction of x hat, and minus L cosine theta in the direction of y hat. And I'm interested in R hat, so R hat would be sine theta x hat minus cosine theta y hat. Remove the L, basically unit length, and dr by dt then sine theta. dr by dt is equal to sine theta becomes cosine theta times d theta over dt times x hat minus, it's plus sine theta d theta over dt is y. Am I writing too small? Is it simple? Okay, it's not working. Okay. D theta by dt doesn't have to be constant, it could be changing with time, but so sine theta x hat plus sine theta y hat, what is that? So if you notice a vector, so this was your r hat. That's angle theta. And if you have this as the angle, that's theta hat, right? Theta hat is actually cosine theta x hat plus sine theta y hat, and that's nothing but theta by dt times theta hat, where I have used the fact that theta hat is cosine theta x hat plus sine theta y hat. That's just so once we have this feature, then we put this in here. So we say that this is L dr, so it's L d theta over dt times r hat, which means that the velocity, if you're constrained to move in a circle, this is not a general motion. If you're the only constraint you have is that you move on a circle, not necessarily uniform circular motion, it could be non-uniform. So it says that the velocity is tangential. So it's, oh, is it tangential? It's theta hat, right? So this is theta hat. Okay. So it's tangential, so it's purely in the theta hat direction. So velocity is always in that direction. If it was not constrained to move in L, then it can move away from that circle, and then you will get another term which will be in the r hat direction. We are interested in the acceleration, and expectation is that there will be a radial acceleration and a tangential acceleration. So acceleration as a vector will be derivative of this. So now I can change derivative of both these quantities. So it is L, second derivative of theta with respect to t, and times theta hat, plus L d theta over dt times d theta hat over dt. And again, now I'm interested in d theta hat by dt. So d theta hat by dt is equal to, take the derivative again, so that's minus sine theta t hat plus cosine theta by dt. Again, take the theta common, so d theta by dt common. And you see that minus sine theta plus cosine theta is nothing but r hat, but a negative r hat. So it is negative r hat. Okay, so that's good. So what we have is L, second derivative of theta dt squared theta hat minus L. And this should be familiar. Right. So we have a radial acceleration, which is this, and this is the tangential acceleration. What is this radial acceleration called? There is a terminology for this. Centripetal acceleration, right? It's a radially inward. So it is inward. So whenever you're going in a circle, in fact, the statement is that you cannot go in a circle unless there is an acceleration in the inward direction. Right? Is it possible to go in a circle without accelerating in the inward direction? Quiz. Quiz is that, can you go in a circle without accelerating? I think not, but criticize, right? Is there a loophole in the whole statement? That's my point. Usually it is said that whenever we go in a circle, centripetal acceleration is inbuilt. Yes.
I was going to say, the engineers, of course, like to make this complicated, and that's the normal acceleration.
I see. But this is the normal. I didn't know that. Okay, good to know. Okay. So they would say this is normal acceleration, and what will be this then?
That's still tangential.
That's still tangential. So normal to the surface, I guess, right? Okay, interesting. Okay, radial inward. Yeah, that's I like radial inward, but yeah, normal. Okay. Interesting. Yeah. So yes, think about, is it possible to, because I make this statement all the time in my undergraduate class that you cannot go in a circle at all, but then suddenly when I'm talking to you guys, it seems, is it possible? Is there a loophole at all that cannot? So yeah, check it out. Probably not, but there's always a loophole, right? There's some constraint, some rule here to switch. This is the tangential acceleration. This is what makes the velocity non-uniform. If the velocity was the same, by velocity I mean speed, the speed with which you're actually magnitude of the velocity with which you're going around the circle, if that remains constant, if it's a uniform circular motion, then this is zero, because then it is the rate of change of theta is the second rate with which theta is changing, then that is zero. In this case, that's that. So okay, so that's your two acceleration. That's what this has to come, right? So this is your AR, if you want. That's AR, and that's a theta. A theta. So let's write the equations again. And then our radial equation is our hat is AR, which is minus, right? So it's minus L d theta by dt square is equal to mg cosine theta minus t. Right, that's here. One of the equations, and the second equation, which is what is usually more relevant in a sense, but the first one is also there. That's a constraint equation if you want. So a theta is L second derivative of theta with respect to t, and that's minus, right? That's equal to minus mg sin theta. It's usually good to I'm missing something here.
M?
M, right? Yeah, M. Yeah. Dimension. I was wondering what is happening with dimension. Thank you. Okay. Good. Thank you. Okay, so M doesn't cancel in the first equation, but the second equation it does cancel. And let's define G over L. It's a good thing to define this to be your omega naught square, right? That's your time period of the or angular frequency of the pendulum. Omega itself is 2 pi over t. So in that terms, I can write our hat is equal to, let's say, m. So let's say t. T is equal to m times g over L ML times omega squared cosine theta, and then this is plus. So this is ML hopefully dimension is okay. And theta hat is equal to, divide this out, this becomes nice. What's the solution to the tangential equation? What's the solution for this? This equation? Second derivative of theta is equal to omega squared sine theta.
Can't be done analytically.
Right, yeah. That it is a hard problem. Yeah, the hard problem to solve. It has solution in terms of elliptic integrals. Yeah, it cannot be solved in terms of elementary functions. I think that might be the statement. So we go, okay, we don't know how to do this. Then you do small angle approximation. Small angle approximation. And the small angle approximation is wherever you see, you keep the leading order. It doesn't have to be theta, it could be theta squared, it could be theta cubed, whatever it is, but you keep the leading order which is relevant. If everything comes out 0, then it's not interesting. So you want the leading order, but you have to be consistent. If you keep theta and you're neglecting theta squared, everywhere you have to neglect theta squared. That's the only rule in the game. And then you say sine theta in that case is equal to theta minus theta cubed over theta factorial and so on. So usually it is sufficient to keep theta. You don't have to keep the theta cubed. So you can replace sine theta with theta, and cosine theta is series is 1 minus theta square over 2 factorial plus so on. Again, if you're keeping leading order until theta, then theta square can be dropped too. So usually you replace all the cosine theta with 1 and sine theta with theta, and that's your small angle approximation. In fact, if you are careful, you'll realize that even the second derivative, even the derivatives, you can replace all with theta and it should perfectly fine. That's conceptually a little harder because these are not known, right? Derivative of the angles are not really known, but you still can make that approximation. So in the small angle approximation, you get r hat is equal to t is equal to m of omega squared, and that's second order, so you don't have to keep it. Right? So that's theta squared, right? Like derivative of theta is the same as theta, so you can drop. So I don't have to keep that as far as I can see, right? So drop that. Theta squared, I don't keep theta squared. That's a small angle. Think so. Check this one, okay? Check this. Quiz, check this. Oh, we will get to check this, right? Because we will actually do this using the Lagrangian and come back on this, right? So we'll get to check this here. So I think this is second order, so I don't have to keep it. So next is second derivative of theta. Notice the difference between second derivative of theta has a single theta in it, right? There is only one angle. The second derivative here, this is the derivative of the angle, but it is squared. So in that sense, it's a second order in the angle. So this is equal to minus omega squared and theta. Theta. Right, that's your equation, and now you know how to solve it. Like based on the initial condition, usually the differential equation is not sufficient to solve an equation. Solve a differential equation, you need some initial condition also. So you have to say how you're leaving it. There are various ways. Two independent ways is that you can start from angle 0, but give it a kick. That's one possibility, or stretch it to a certain extent and leave it. So those are two independent ways, but then there is a whole combination of those, and you can solve this, and it's an oscillatory problem, right? This is oscillatory solutions, and one can work on this. So that's your that's how you will proceed in the Newtonian equation. And notice there is this T that shows up everywhere. But now we say, let's go back again and redo this problem, this time using the idea of the Lagrangian. And the main idea there is that you realize that this mass is going to go on the circle. It's constrained to go on that circle, right? That's the basic idea in there. So let's do the Lagrangian now. So, well, let's say Lagrangian. And the primary idea in the Lagrangian is that find a constraint. So there's a constraint. So, and the constraint seems to be that if I have a coordinate system, in general, I have X and Y coordinate system. So that's X and Y. X square plus Y square for this mass, it seems to be equal to L square. So that seems to suggest that you don't need two variables. You don't need two equations. There is only one equation needed. The second equation is just a constraint. So second equation is not very useful, or it's a baggage you're carrying with it. Can we get rid of it right in the first step itself? That's the idea. Right. So you always in a Lagrangian, you look for a constraint like this, and then you say that, okay, if there is a constraint, what is actually dynamical? And you say that, okay, this is the angle theta that's changing. That's the only change. So identifying that parameter that's relevant for the problem is crucial. So here, identify theta. So we have to decide that we are going to work with angle theta, and that's usually the hard part. Like this system we know already. If you know a new system, if I tell you, for example, the magnetic field, right, electromagnetism, what are the independent quantities there? That can be challenging as to what exactly I use as an independent variable, and this is called a generalized variable. Generalized coordinate, actually, not variable. Often this is also called the dynamical variable. That's the quantity that changes with time. So that's like I like to call it the dynamical variable, but it's almost in the modern last 50 to 70 years, it's very common to say generalized coordinate. So it's perfectly fine to call it generalized coordinate. It's very universal in a sense. Okay, so how do we proceed? So if we know these quantities, how do we proceed? The basic idea would be the same we want, but here the goal will be the Lagrangian is the kinetic energy minus the potential energy, right? Remember that. So that will be our idea. So just that we have to write everything in terms of angle theta. So we want to write Lagrangian as a function of angle theta alone, and actually theta dot, and if necessary, put a time also in general. So the moment you have identified this generalized coordinate, then your goal is to write a Lagrangian, which is a function of theta, theta dot, and t, and this will be kinetic energy, which can again be theta, theta dot, and t in general, but usually it is only theta dot, at least in this system, and minus the potential energy, which is always only theta and t. Quiz for you guys. Can you have potential energy, which is, no, we do have, right? Magnetism has velocity. And yeah, you can have velocity, but typically it's not common. Yeah. You have velocity, of course. Yeah. So no quiz. Okay, kinetic energy we say is equal to half. Let's begin with the standard notion. So that's half mv squared. That's your. But we want to write this in terms of angle theta. That's our goal. And potential energy is equal to mg y, right? So it's the gravitational potential energy. So it's mg times y. G is acting downward, so mg times y. And now we want to convert all this. So v is dx by dt plus dy by dt. So we want to convert everything in terms of angle theta. That's the goal. So let's have a diagram. So we are having, that's our angle theta. This is x, that's your y, and that's your mass m. And even though x hat, y hat, let's say. And that's, let's say, x comma y. That's the coordinates of that mass. What is x and y? X is equal to, you want to write everything in terms of theta, notice. So x will be the position here, so that's L sine theta. And y is equal to minus L cosine theta. That's right. So immediately we know the potential energy then, right? So it is minus mgl cosine theta. So we know the potential energy in terms of angle theta. So that immediately tells me that this is minus mgl cosine theta. My goal was to write the potential energy in terms of the generalized coordinate, and that's minus mgl cosine theta. Now the idea is to write kinetic energy also in the same term, same angle theta, but this is all x, so we have to take the derivative, right? So dx by dt, x by dt is L cosine theta times d theta by dt. And dy by dt is equal to minus of L sine theta by dt. So once I have identified the x and y. Okay. So you have kinetic energy is equal to half mv square, which is half. So it's half mv square. That's half m dx by dt square plus half m dy by dt square. So you basically have to square this. So that's half m l square cosine square theta by dt square plus half m l square sine square theta by dt square. And that's it. But this is cosine square is 1. So that's equal to half m l square theta by dt square. Often it is a good notation. I think at least in this context, when the time derivative is the only thing involved, it is often the notation that time derivatives are represented by theta dot. I don't use it very often, but sometimes in these kind of equations, especially when we get into double pendulum, there will be a good number of derivatives. So I will sometimes use it whenever there is no ambiguity at all. It is okay. So okay, so now we have the Lagrangian. So L is equal to L now is a function of theta dot, and there is no t actually. So still let me write that here. So that's your half m L square, right? This is theta dot square. And your potential energy has a minus sign already, but becomes plus energy. Why did that come out plus energy?
Is it the way that we define the axis system?
Is that the problem?
Because our y is below.
Y is below, but it did come out negative, right? So it was in the y is positive there. It's okay, probably, right? Kinetic energy. Yeah, the derivative of cosine theta has sign minus, right? I think it's okay. Yeah. I'm gonna be should be minus. Notice that there is no explicit time dependence in this. So even though Lagrangian in general can be time dependent, so there is no, in our problem here, there is no time dependence. That's just an observation you can make. It's a time independent Lagrangian. And yeah, great. So that's your Lagrangian, one of the simplest Lagrangians you can have. It's also good to right away here at this point, you can say that you want to keep only the leading order and angles. Now, notice, so at this point, so small angle approximation. So small angle approximation can be done. Say something about this small angle approximation can be done at the level of equation of motions, or so if you are doing the small angle approximations at the level of equation of motion, then typically involves order theta. Order theta is involves theta, like angle theta. Let me just take angle theta. But if you can make the small angle approximation at the level of Lagrangian. If you want the Lagrangian itself in small angle approximation, that's a possibility. Why not? Right? But then you are losing information right at this level itself. Often you don't want to do that because it is it's good to have the Lagrangian as far as possible, keep the exact one. But if you're used to the whole thing, if you know the system very well, you say that I don't want to carry on the baggage, so you can do it right at this level. But then you say typically involves theta squared. So you want to keep everything to theta squared. For example, if I were to drop theta squared and this, the Lagrangian is gone, right? So this is theta squared, cosine theta is 1, so it's just MGL, that is, it's a constant Lagrangian. There's nothing in that, right? So we want to keep it to theta squared. So let's do both ways, right? Let's keep the Lagrangian to the full, and then I will come back and do the approximation. So this is an observation, but let's not go into an approximation at this point. I'll come back to that. So first thing you do is canonical momentum, right? Canonical momentum, or just momentum in this case. Standard mechanical momentum is P. In this case, P theta, right? It's good to emphasize that this is P with respect to theta. So that's equal to the Lagrangian with respect to theta dot. Like the velocity, the derivative with respect to the generalized coordinate is your velocity, if you want to call it the velocity. Generalized velocity. That's here, so that's M L squared theta dot. And what is that? What is the name for this in Newtonian physics? This should be familiar. Angular momentum, right? This is angle. This is the momentum associated with the angle. So that's the angular momentum. And so that's canonical momentum. So let's call, I don't think this is standard, but why not? Let's say canonical force. Canonical force will be canonical force is not derivative with L. Canonical force is negative potential energy with generalized coordinate. And in this case, it is equal to what is this? Minus of, that is minus and a minus, and then I get a third minus when I take a derivative. So it is minus mgl sine theta. And again, how would you identify this in the system? The generalized force. The generalized momentum or the canonical momentum is angular momentum. What is the force associated with the rate of change of angular momentum? Is torque. So this is angular momentum. And this is the canonical or often you say generalized momentum. Generalized. I think generalized is getting more common in the modern, like in the last 50 to 70 years, it's common to say generalized, but in the older textbooks, 100 years back, it was more canonical momentum and canonical force. So this will be the torque. Right, so this is, if you notice, this is mg crossed with r, right? So torque is mg crossed with r. Okay, so that's your identifications immediately, but let's go ahead and write our Lagrangian equations. Euler-Lagrange equation is d by time derivative of the canonical momentum is equal to time, partial derivative of the generalized coordinate of L. So that is the same as, so we said d by dt of m L square theta dot is equal to dl by d theta is here. So it is directly I can do that here. It's actually the force that will come in. This is the rate of change of momentum, if you want. So this will be minus mg L sine theta. And you immediately see that ml cancels out, we'll divide it out by, this is theta double dot is equal to minus omega square sine theta. I'll make the small angle approximation. Oh, before that I should point out that notice that in the Lagrangian formalism, there is no mention of the force of tension. Force of tension did not appear anywhere. That went away right in the first statement when I put the constraint there. The idea of the constraint took out the force of tension. Force of tension principle in the Newtonian mechanics is there to put the constraint. There we are modeling it in the sense that we want that constraint. So the force of tension does a job of providing that constraint. Here, the main idea is that there is no force of tension, the angle, the equation in the radial direction is not there at all, right? It disappears completely because that's not a dynamical direction at all, if you want. At this stage, if you do small angle approximation, you get theta double dot is equal to minus omega square theta, which is our equation that you would have got from here. But I suggested that what if we had done this right from the first place itself? So let's do the small angle approximation to L. Right? L is equal to, if I were to write only the leading order, so I would say this is 0. So that is, this is second order, right? So this is second order plus mgl. And then there is order theta, right? Is that theta of theta? This is curly O, right? This is order, right? So that's the order to theta, the first leading order. That's not useful at all. There is no variables in there. That's a constant Lagrangian, not useful. not useful. So let's say, okay, I keep the leading order. In fact, I can write theta square, right? This is not even theta. There is no leading order in theta. So it's after the first order, after the constant order, it's coming is theta square. Keep the second order, then I say that, okay, so L is equal to the second order. This is half m L square theta dot square plus mg L. This is 1 minus theta square over 2 plus order theta cube if you want. I have neglected everything to order theta cube. That's the same as of m L square theta dot square minus of mg L theta square plus mgl plus order q. And this constant, of course, will not play any role because that neither has theta, neither has derivative of theta. So in all the terms, it will go away. And that reminds you of harmonic oscillator, right? So there is a velocity term, kinetic energy, which is squared, and potential energy, which is squared. That's the harmonic oscillator. And that's why it is oscillating. So that it's oscillation in angle theta. And now again, you do the momentum and all. So this is p theta now. So canonical momentum is dl by d theta. And that does capture the full angular momentum. But what about the torque? So it is minus du by d theta. That's equal to, I should go back here, right? So this is minus 1 minus, so it is minus d by d theta. U is minus mgl. So that's minus mgl cosine theta, that's 1 minus theta square over 2. Minus plus, so this is time derivative or theta derivative of mgl minus of mgl theta square. And this is equal to 2 goes away, that's minus mgl theta. And which is an approximation of this sine theta, an approximated. But this should remind you of the spring constant, right? This is the force, generalized force, and this is the spring constant minus kx, right? F is equal to minus kx. Right? Linear in the variable. The generalized variable is angle theta. Here, this comes out as a spring constant of the Hooke's law shows up. And finally, once you have this, what's your Euler-Lagrange equation? That's dl by d theta dot equal to L by d theta, and that's immediately d by dt of m L square theta dot equal to minus mg of theta, and this again gives you theta double dot is equal to minus omega square. And that's of course a simple system, but it's a good to do a simple system where you see all the properties of the Lagrangian coming in your homework. And on Thursday, I'll do a double pendulum where this will be a little more complicated, but still the features will stay. Here in the next 15 minutes, right? I have about 12 minutes. Let me at least pose a problem. It's an interesting problem. Or before that, I think questions on the comments should be hopefully emphasizes most of the points. So let's keep the same things. Yeah, so yeah, let me call this the inverted pendulum. I doubt if I will be able to finish this. All right, if I don't finish it, I won't stretch this into the lecture, next lecture, if you allow me to do that. Okay, the expectation is that you go back and do it. But I'll tell you something interesting about this. Maybe you guys have heard this before, or I have told you this. If you have a normal pendulum, if you have a normal pendulum, this is a normal pendulum, and what are its stable points as far as angle theta goes? Okay, that means to say that about which angle will it oscillate? Right? So it is theta equal to 0, right? About theta equal to 0, it keeps oscillating. What about theta equal to pi? Like if I put angle theta equal to pi, is it stable then? It's not stable. You're familiar with stable and unstable, right? It's basically an upside down parabola, so it will go away. So it's a decaying system. It will not stay there at all. Right? But that's not always true. There is a very special way you can make it happen. And actually, there is this interesting. Let me see if I can pull this out. Yeah. So you have this. You might have balanced this. Sometimes you kind of balance it, right? So you can balance that. And now the idea is that when you look at it, you do get it balanced, right? And often you say that you're actually moving it around. So so the idea is that what if you oscillate this horizontally? So you oscillate this with a certain frequency horizontally, and the question is, will it stabilize? Okay. And the answer is no, it will not stabilize. It seems like it's stabilized. That's because you're looking at that, right? You're actually, that's a feedback mechanism. There's a faster one. But what is interesting is that now you do the same thing vertically. Okay, so you're doing this vertical oscillations, and for small oscillations, it will not stabilize. But there is a critical frequency beyond which it will stabilize. Okay, so that should show up here. And by the way, this was, I taught this, I think, a few years back in the lecture. And Dustin, he's a grad student here. So I said that, yeah, maybe one should build this. And Dustin went back and he had his ball bearings and all that. And he actually built this using a nice, he used the output from sound waves for the frequency. And he made a simple pendulum which actually does it. And he still has it in the lab. So if you are interested, go and ask him. Sometimes I've asked him to show this in the open, sometimes now it is standard. You guys are all during pandemic. We used to have this open house where high school students come and we exhibit or we show some exhibits of some simple experiments or demonstrations. So he did that and it was reasonably popular, like people like the fact that things can be made upside down. There are some applications of this. I don't know, I think maybe Segway, I've heard that uses this concept, but I'm not sure. I wouldn't be surprised if they really use the feedback mechanism instead of, this is not a feedback, like you can be blind and do this and perfectly this will always, and you can actually push it. It is really stable. You can touch it and push it and it is really stable. So let's write the Lagrangian for this and what really happens, and it's easy to write the Lagrangian and it's easy to see what really does it. But again, the solutions are not easy, even in a small angle approximation. The small angle solutions are not easy. It is given in terms of what is called Matthew functions. the normal pendulum has elliptic integrals. In small angle approximation, the solutions for the inverted pendulum is given in terms of Matthew. This was started by this whole problem. The idea was that moon is having an orbit around Earth, and the question you ask is, what if you perturb it a little, right? If you perturb the moon a little, goes this way, that way, is it possible that it can become unstable? Is it possible for the moon to become stable? And this was first time done by, I think, Hall. Hall was the first person to do it in 1880s. That's an interesting problem. I was interested in it for some time, so that's why I'm telling you it. So now what we are saying, so how do we do this here? So the point is we have the same axis, and now we have this pendulum, which is here. Let me draw this again, sorry. So in general, the pendulum doesn't have to be at the origin, that's in here. So let's have it constrained on the y-axis. You can do this for the x-axis also, but let's have it constrained on the y-axis. So that's your x and y. This is also x hat and y hat, and this is x comma y. And let's have this motion here. That's your A, let's say. Or what should I call this? X naught, right? Or y naught, 0 comma y naught. Right? That's your height with which you move. And how do you model this is y naught is not an arbitrary y naught. Let's say, yes. Oh, sorry. Thinking. Okay. So y naught here is not a constant amplitude. This you oscillate, right? So this is your y naught times or maximum, right? A, let's say amplitude. Y naught here is amplitude times, let's say, sine omega t, sine omega naught t. So this is the what do you call this? Forced vibration, right? This is the forced vibration. So you're vibrating this pendulum in the vertical direction with this frequency, and we are choosing this to be a sine. Okay, so what's your coordinates? Right. So you start by writing your x and y, right? Again, the constraint is there. It's a circle x squared plus. So now, or maybe I should put the constraint here, right? The constraint is x squared plus y minus y naught squared has to be equal to L squared. Very similar constraint, except that now it is y minus y naught squared. X is equal to L sine theta, right? L sine theta, that remains the same. Y is equal to L cosine theta minus L cosine theta plus y naught, right? Plus y naught is A sine omega t, omega naught t. Is that clear? So A sine omega t, and then subtract out the minus L cosine theta. Okay, so then x dot velocity, that's what you need, is L cosine sine theta is L cosine theta, theta dot. That's what we did there. And y dot, coming to rush here, so it's 4 minutes. So cosine theta is L sine theta, theta dot, and plus omega naught A cosine omega naught t. So that's your additional term, if you will. Kinetic energy. Kinetic energy is equal to sum this up. So half m v squared. So this is so half m L. So this is L squared cosine square theta, theta dot square, plus L sine theta, theta dot, plus omega naught A cosine omega naught T square. So that's equal to first. So the square term has this. So cosine square theta is surely there. That's theta dot square. That's there. Then we have plus half m omega naught square A square times cosine square omega naught T. And then there is a cross term plus half m 2 times L times omega naught A sine theta, theta dot cosine omega naught T. Okay. So it becomes a little lengthier. There is this term, this term. Notice that this is time dependent. Right? Unlike the earlier case, this is a time dependent Lagrangian. That's your kinetic energy. And your potential energy is minus mg, no, minus mg plus mg, right? It's plus mgy, and y was equal to mg minus L cosine theta plus A sine omega naught T. Kinetic energy and potential energy is there, then you can immediately get the Euler-Lagrange equation. So let me write that down here in 2 minutes. Okay. I'm already 1 minute maybe. So I have to take the derivative with theta dot. So that's ml square theta dot for the Lagrangian. So that's only this term. Theta dot, right? Oh, there is this also here. The 2 cancels ml plus ml omega naught A sine theta cosine omega naught T. Right? And theta dot is not there in the Lagrangian, sorry, in the potential energy. So that's your canonical momentum if you want. Time derivative of the canonical momentum is Lagrangian with respect to angle theta. So this is derivative with theta. There is no theta here. There is no theta there. There's theta here because there is sine theta there. Oh, I should have done that small angle approximation right here. That's nice, but I didn't want to. That's the full thing. So sine theta, theta is down here. So that's so it is m L omega naught A cosine theta, theta dot cosine omega naught T, and minus u. So minus makes this a plus. So it's minus mgl sine theta. I think that's what your equation is. And if you were to do the derivatives now, maybe at this stage, put the small angle approximation. Yeah. So this is theta double dot ml square. Here, small angle approximation makes this theta, so that makes it theta dot. So that's plus ml omega naught A theta dot cosine omega naught T, and that's equal to the same term on the right side. But now I have to take 1 minus. So it is ml. So it is minus ml omega naught A. Cosine theta is 1. That's theta dot cosine omega naught t minus MGL t. Pull this onto the right. And what I have is, probably 2 more minutes. Sorry. I can finish this. So M can be got rid of, L square can be got rid of theta double dot and M L square. So there's omega naught A over L. Which is plus 2 omega naught A over L. And this is theta dot. It's cosine omega naught T theta dot. And we have minus MGT. So minus omega squared. All right. So this is the additional term that you get. So notice this perturbation. So you're changing that frequency. The idea is that for some average value, this can compensate that gravity and take the gravitation in the upward direction. The interpretation is harder. We'll have to come back to that at another point. But very broadly, you get the whole example where you can do this in a very quick 5 minutes, in a very short. So I'll stop here. Sorry about the hurried way of proceeding on the last. But you get the idea. Next time we'll do the double pendulum and see some physics out of it at the end in the small angle approximation. Thank you. And check this work. I might have made mistakes in the. It seems okay.